In this video, we will look at the concepts of impulse and momentum. Previously, in the work energy theorem, we related the net work on a system to the change in kinetic energy. That is, we showed that if you apply a force over some displacement from some initial position to some final position, it results in a change in kinetic energy, where kinetic energy is given by 1/2 mv squared. But what if, instead of applying a force while the system is moving from some initial position to a final position, you apply a force while the system is going from some initial time to some final time? So to look at this, we will introduce a new quantity called impulse. So just like work was the integral of force with respect to position, impulse is the integral of force with respect to time. Notice that unlike work, impulse is a vector. Work was a scalar because we had a dot product between the force and the displacement. Here we have simply f, the vector, multiplied by the scalar quantity dt. So the quantity overall is still a vector. So what is the effect of impulse? We will follow a path similar to the work energy theorem, and we will arrive at the impulse momentum theorem. So just like the work energy theorem looks at the net work, for the impulse momentum theorem, we look at the net impulse. So in this case, the force that is being integrated is the net force. By Newton's second law, we can replace the net force with simply mass times acceleration. But acceleration is dv over dt. So we have dv over dt times dt, so that's simply dv. So we have the net impulse is the integral from initial to final of m dv. M is a constant, so we pull it out. So we have integral m times integral initial to final of dv. That's a simple enough integral. And so we arrive at the result. The net impulse is simply m times v evaluated at final and initial. So it's mv final minus mv initial. So you can see that we are very naturally led to define a new quantity, which is momentum, which is simply mv. And traditionally, we use the letter p for momentum. So we have p final minus p initial. To summarize, we have shown that in the impulse momentum theorem, the net impulse on a system, which by definition is the integral of f net with respect to time from initial to final, is equal to the change in momentum, where p equals mv is the momentum. And notice that momentum, like impulse, is a vector quantity. We will see later that one of the reasons why momentum is such a useful concept is that under very general conditions, the momentum of a system will be conserved. And because momentum is a vector, we really get three conserved quantities all at once.